Okay, so welcome to the 8th lecture of this energy system modeling course. And I'm just going to check from Zoom that can I get a thumbs up if you can hear my voice. Yes, that's good. And remember that we're going to be starting the SpineOpt project work next week. I'm going to upload the template and the instructions for you this week, so you can get already familiarized with that. And if you want, you can download the SpineOpt for your own computer as well. And Anna Mutula is going to be giving her guest lectures. She has 3 lectures, so it's starting from next week. And I will be streaming it in this classroom, so you can come here or watch via Zoom. So she won't be coming physically here, but we'll have a Zoom connection, and I'll put it on the screen. And remember, there is the Moodle assignment 3, and Moodle assignment 1 and 2 have closed, and this is available till 18th of this month. And now you already have, for the project work, you have the required data collection sheet in here. So you can see what kind of data do you need for the project work. But on today's lecture content, we're going to be going through aspects on this dynamic modeling of these energy systems. And to some extent, we have been doing dynamic modeling. So dynamic modeling is where you're taking into account the history. So you have something, it's not just time series analysis. So in time series analysis, you have an aspect of time moving forwards and you're analyzing it step by step. But in this dynamic modeling, you are taking into account what has been happening in the past, and it's going to affect the future. So, for example, the energy storage was this kind of a dynamic energy system modeling. But the ones that we have been making, for example, the electric market or electricity network in Moodle assignment 2 and in our exercises, that wasn't in a sense dynamic. There was a time series, but nothing from the previous steps didn't affect to the future steps, and also there wasn't any kind of a market interaction. We had just a fixed demand, and that wasn't anyhow influenced by the price. So in that sense, that wasn't anyhow dynamic. And in the exercises, we'll be going through a simple example on how that market interaction could occur. And these dynamic elements, they can occur or they can be included in these energy sources. So you can include some modeling aspects in the sources themselves, the transmission, the storage, and the consumption. So we'll look all of these in this lecture. And we're going to check before I start moving forwards that I do actually have the recording on. Yes. Yeah, so an energy system, it could be considered as a dynamic system if it accounts for changes over time. So variables evolve based on past states, and that is taken into account with differential equations, for example, in the case of energy storages. So whatever happened in the past is going to affect the future. And no time step is just being treated as independent time slice. So typically done through time stepping. That's what we are doing in multiple courses. So whenever you have differential equations and you're trying to solve them numerically, you have these time steps, and what happens in the past affects the future. So it's the same thing in here. And so it works. Yeah. So key characteristics. You have these temporal dependencies. So time goes by, and whatever happens in the past affects the future. So models outputs are given time step dependent variables that affect the calculation. You have storages and ramp constraints, for example. So these the storages we have been examining to some extent, but for example, these ramp constraints we didn't take into account in our, for example, district heating modeling. So whenever you're going to put a facility on, where it be, for example, a bubbling fluidized bed, it's going to take multiple hours to get it ramped up from 0 to 100. And even when it's up and running, these ramping constraints during this hot run, so whenever it's close to 100, you're going to ramp down. It has a certain time that it takes to ramp down to, for example, 50%. And that's been kind of like an area of great interest during the last decade, because then these in the last decade there were a lot of these ideas that the renewable energy would be increasing, and biomass plants especially would be the ones to kind of adjust for those loads, along with the water power plants, hydro plants. So these include constraints on energy storage and ramp rates. And then you have optimization over time horizons. So that's a key aspect of those. So, for example, this rolling horizon or multi-period optimization to make decisions on what to do in the future. And simulation of system evolution. So you have the model constructed, you have different submodels, and then you simulate it over a certain time with certain scenarios. So this was the picture that I've been showing you in almost every lecture. So the energy system, you have the source, you have some kind of a conversion, transmission, storage, and consumption. And all of these can have these dynamic elements in them. And if we're starting to look through the energy sources, so you have the fuel supply, for example, you have the renewable resources, dynamic elements that are included in there are fuel availability and depletion, especially, for example, with biomass. You have a certain supply chain. You're harvesting biomass, you're harvesting peat. It has a certain growth rate with the biomass. And for example, if you have this peat, it has a seasonal variability because it's hard to harvest at certain times of the year when the bog is mushy, and the same goes for the forests. So biomass is more easily extracted at certain times of the year. So that affects the fuel availability and storage depletion. So seasonal variability, intermittency and variability, wind, solar, hydro availability. So that is going to fluctuate over time based on weather. And we do not yet have these kinds of perfect weather models that would predict it far into the future, just a few days or a matter of weeks, especially in Finland due to our weather patterns. Fuel supply chains. And there is a lot of literature on this one. This is a really interesting topic, how to kind of optimize these fuel supply chains. So how much time delay is there due to logistics related to like biomass harvesting, drying, and transport? And then market-based pricing. So the interaction of the consumption and the prices. So whenever you have more consumption, what's going to happen, you're more likely to deplete your fuel storages, and the availability is going to decrease. So it's going to affect the prices. And that's what's actually been happening in Finland with biomass recently. So this intermittency and variability is something that we look through with the lectures related to this renewable energy production. So you had some intermittency with wind and solar, and this was the example that we went through in the exercise classes. So this was just an Excel calculation. You had some kind of a consumption profile, and then you had solar and wind intermittency. And based on the variability of that, you could take that into account with this Weibull distribution, for example, and make this kind of a Monte Carlo simulation that I showed as an example. So this, in a sense, was a dynamic energy system model, since we had these storages or a storage in there. So it has these spikes in here on the upper corner, the right upper corner figure has this storage, so state of charge in essence. So that makes it a dynamic energy system model. Otherwise, it would have been just one time step analysis, one time step analysis, and so forth. So there's no dynamic effects in there. But this, for example, doesn't take into account anyhow the market prices and the effect of this system on market prices. This is such a small system that it, in essence, doesn't have any effect on the market prices. It cannot, for example, consume so much diesel fuel that it will affect on diesel fuel prices. But whenever you are scaling up to country level energy system models, then the market prices will be affected by the consumption. These fuel supply chains, there are multiple of these. As I said, there's a lot of literature related to this one that is rather interesting. So there are these different kinds of supply chains that you can model, centralized, distributed, so this linear type, and then there can be this kind of a hub and spoke type. So you have multiple kind of sources to the this centralized upgrading center or upgrading and co-refining plant. And there's a couple of publications that I put in here, and the other one represents a really good idea on how you can scale up the analysis related to this biomass modeling. So starting from the molecule, you have the reaction pathways and so forth that affects to, for example, the heating value of the system. So that's one area of study. Then you have the process in which the biomass is either upgraded or consumed. You have the process modeling, and our energy engineering students are mostly familiar with these two steps. But then you have the supply chain and the whole ecosystem that you can take into account in the models. But for example, this kind of a supply chain, you can have, for example, in these smaller kind of there's this hub and they call it in here hub and spike network. So on these spikes where you have the kind of initial production, you can have either some submodels in there, or you can have some time series that this actual location produces with a certain amount during the year of this wanted biomass type. So from there on out, you can start constructing the supply chain model. And what, in essence, your energy system model is going to see, it's going to see when biomass is available and at what times and how much of this fuel is available. So there, for example, I didn't find such figures on Finland. This was really nicely analyzed. So there is different kinds of biomass and their availability in Germany on a monthly basis. So you can see this seasonal variability. So this would be a perfect example of the input on our energy system model. So this kind of a biomass would be available for the production plant with during the summer months or maybe in the spring months, and the other one more during the winter. But I didn't find such information from Finland. It was really hard to find any kind of seasonal variability related to these fuels, but that doesn't mean that it exists. It's just hard to find that data. So to accurately represent this kind of a fuel logistics and supply constraints, at least you have to consider these kinds of time delays. So if you harvest the biomass during this time, then it has to sit and dry for a while. It has to be transported. There's going to be lags. There's going to be lags in fuel availability. And that is going to affect your dispatch decisions. But in the model, most likely you would have a time series that represents the availability of that certain fuel. So seasonality and availability. So that was the previous figure. Storage and inventory limits. So power plants can stockpile fuels, but limited storage capacity creates these additional constraints. So if you have seen, for example, how this kind of a small district heating plants, let's say 1 megawatt plant operates, it's a great firing boiler, and there's a truck that carries wood chips into there, and the process is fully automated. So there's going to be a silo in there, and the wood chips are dumped into the silo, and there's going to be a screw feeder that inserts the fuel from the silo to the boiler, to the grate. So it's an automated system, but it has to be replenished depending on the storage size and the consumption. So supply chain distributions also, weather conditions, transportation issues, and policy changes, as in Finland you have seen, can cause sudden fuel shortages. And fuel quality varies. Hard word in English. So there's going to be changes in, for example, the heating value. So that's going to affect also the operation of the system. So depending on how small, how in depth and how detailed model you're going to make, these are issues that also concern like on the single production plant level. And for example, this biomass availability, you could make such a simple model, for example, that you have a load in here. So your production should be something like this. So the consumption, I just put a sine wave in there. And what I have in here is I have a storage that is going to be replenished every single day with a certain amount of biomass, and there's going to be an initial amount of that biomass. So in essence, that's a energy storage. So how big of a fuel pile do you have in there? That's going to be your storage size. So you can calculate how much energy you have in that storage. It's the same as vehicle fuel tank. And usually these biomass storages compared to like coal storages, coal can be left out in the open. But for example, let's see if I can find from Google Maps. I can fast find this Vuosaari, I'm searching for that in here, and they have the power plant, and I find it from here. Is it in here? Yeah. So there's the biomass silo. Let's check it out from the here. So it has a certain amount of size. So whenever you have a biomass site, biomass combustion site, you're most likely going to have some kind of a silo in there that has a certain size, and that is in essence your energy storage system. So in this case, my biomass replenishment cycle cannot kind of meet the demand that is needed. So in here, the initial storage amount that you had is going to almost be enough, but then the replenishment cycle isn't fast enough. So what you would have to do is you would have to, for example, decrease, let's bring in every 14 hours the fuel, and let's see what happens. Yeah, so now our demand is met and our storage is going to be overflowed. So a simple model, but it just shows you how to take this into account. So you can have a certain time delay in between the replenishment cycle. And on this market-based pricing, this is a really interesting thing in my opinion, because this is a perfect example what's been happening in Finland now. Since, for example, this district heating, district heating production has been making this transition from fossil fuels to biomass. There's been this electrification. So a lot of these electric boilers have been installed in just a couple of years. They come from this Norwegian company, Parat. I was in UPM Tervasaari yesterday or Monday, and they were showing this steam producing 60 megawatt electric boiler that they have been installing in there. So a lot of these facilities that utilize district heating or process steam can utilize those. So either way, biomass still has been replacing a lot of this natural gas, peat, coal, oil, and actually the Google Map image that I showed you, this power plant in here, it's a heat-only boiler, little less than 400 megawatts, just biomass. No electricity, just heat and just biomass. And what's been happening in the few years in here is that biomass price has been coming up pretty much. So development of the average price of district heating according to the main fuel. So you can see how it affects the district heating price as well. So on a kind of broad scale, longer scale, time frame, you have to take into account these effects that if you're going to increase biomass consumption in your district heating production fleet, or for example, in this Moodle exercise 2 that I said gave to you, that increase some production type. If you're going to increase biomass, what it's going to do, it's going to generate kind of market disturbance that's going to make the prices go up. And that's what's been happening. And also, there's been a lot of, or at least some other issues that affect this. So increased demand, loss of Russian natural gas due to the war. So gas imports and the phase out of coal and peat. So those have been already decided that, hey, we're going to phase out. We're going to decrease the amount of coal coal-based district heat production and peat-based district heat production. And district heating companies rely more on biomass. For example, Tampere, Naistenlahti 3, that's a perfect example. Households also turn to biomass, including me, because the electricity was so expensive during 2022. And also due to the post-corona kind of industrial resurgence, what happened is that coal and natural gas prices went up. So supply disruptions, so sanctions cut off Russian wood chips and pellet imports. We didn't have the Russian biomass that we could rely on. Reduced logging and changes in the forest management, limited domestic availability, and it's also competition for sawmill byproducts. So rising costs, fuel and transportation costs surged because oil prices and natural gas prices went up. And there's going to be also export competition. Some of the European countries were also relying on Russian energy, so Finnish biomass could be used for that. And then there was stockpiling and speculation. So that was a perfect example on this kind of a what happens in the markets when consumption increases and there are certain disruptions in the system. I don't know if there was anybody that could have kind of seen this coming and modeled this to the extent that they could kind of take measures in advance, because I don't think nobody saw the Russian-Ukraine war before it occurred, in a sense that you could have been ready for this kind of market disruptions. But that's what happened, and now we are dealing with really high biomass prices. So wood chips are costing like 40 euros per megawatt hour nowadays, and it's crazy expensive. Conversion. So power plants, boilers, CHP units, what dynamic elements do they contain? So in terms of these market effects, electricity market, in a sense, it's easier to take into account what's happening in there. These supply chains related to this district heating systems, they are so complex that it's really hard to start modeling those, especially in this course time frame. But that is being done nonetheless. But related to power plants, you have ramping constraints, you have efficiency changes, wear and maintenance cycles, and operational delays. So this kind of a thermal inertia on boilers and steam turbines. I'm not going to, by the way, cover all of these. For example, I don't think I have anything on this operational delays. So I have kind of the most interesting aspects of these. So ramping constraints. This refers to the plant's ability to adjust their electricity or district heating production output in response to changes in demand and supply conditions. So you have a certain startup time, and then you have a certain minimum load. For example, with electricity, it's just the amount of steam that you have to produce to get the turbine running. Then you have a certain ramp rate, and that is something that it's really hard to kind of deduce based on modeling. So usually you're going to have certain ramp rates, average ramp rates for those plant types. So it's good if you have a time series based information on how fast you can adjust a certain power plant. Otherwise, it's really hard to kind of assess. But based on the plant type, you can use these average values. So ramp rate, the speed at which you can increase or decrease the power plant power. And startup time, duration required for a power plant to go from shutdown state to full operational capacity. And then you have, for example, nuclear power plants that have this due to the xenon poisoning effect. If you shut it down, you have to keep it, is it at least 3 days that you have to keep it shut down, and then you can ramp it up. So certain power plant types have these kind of additional constraints due to their technology. So startup time, it can just be related to, for example, how much do you have to heat how fast you can heat the boiler due to thermal expansion, that you don't break it to start producing steam. And for like coal plants, it's a matter of, let's say, 8 to 12 hours. And with these electric boilers, it's like matter of minutes. You can ramp it up from 0 to 100% in a matter of like 1 minute. So that's a really fast system. Minimum load, the lowest power output you can produce with the plant. And there's, for example, open cycle gas turbine, combined cycle gas turbine, state of the art and commonly used. So there's a kind of discontinuation due to the fact that there's gas turbine and there is the heat recovery steam generator. So they have different kinds of ramping rates. And then there's the hard coal plants, which are the slowest one. And as I said, this is a rather hard thing to kind of find for an individual power plant. So you would have to have this historical or time series data for it. But you can use average values. And how that affects to the energy system modeling. So whenever you have, for example, in a district heating system, we could make these ramping constraints that you cannot, and especially in the startup, you cannot start the system in just a matter of seconds. It takes, for example, 8 hours, and it has a certain cost because you have to use, for example, these oil burners to heat up the fluidized bed itself. So you can apply certain fuel costs for those heating up and then shut down cycles. So efficiency changes. I found a couple of these systems. So this, you can see there is a grate firing boiler, so furnace in here, and it's in a bit more detailed manner described in here. And what in this article they were determining was the efficiency of the system. So how much heat could be input into the from the fuel to the steam or the water. So you can see that there's maximum and minimum expected, and the measured was barely somewhere in between. So one point was a bit up. So it's always not as straightforward as looking from the manual that, okay, these are the values. Well, they were, but they weren't that exact. And what happens with usually with power plants or this energy production is when you operate the system at partial loads, it means that the efficiency decreases. So this is, for example, this kind of a gas turbine. So open cycle gas turbine, compressor combustion chamber turbine generator. And there's cooling air, by the way, being put to the turbine so that the blades don't overheat. So what happens when you decrease the load or go into partial load operation, the efficiency decreases. And you can see it starts from somewhere around 40 and decreases to below 30. So gas turbines have notoriously bad kind of partial load efficiencies. That's That's not the case, for example, with engine power plants, because you have modules. You can shut down this module, and this module, and the other ones are operating at full capacity. So most likely, if you were to take this into account, if your power plant or heat production plant operates at partial loads, you're going to have a linear fit for it. So whenever you decrease the load, it has a linear decrease in the efficiency. But as you can see in here, it's more like parabolic. What else? Wear and maintenance cycles. And this could be taken into account in your this model assignment 2. For example, you have a time series of availability from this nuclear power plant. It's 0 or it's 1. It's down or it's up. So available or under maintenance. So for example, nuclear power plants, they operate under strict maintenance schedules. And by the way, Olkiluoto 3 at the moment is being under maintenance. So that is going to affect our electricity prices, as you can now, with this model assignment 2, start testing that. Let's take out nuclear power plant. Well, the model assignment 2 isn't that good for it, since you were running Finland as an island, but the exercise that we did earlier. So you can just say we had these capacity factors for the renewable power plants. So wind and solar. I guess we didn't touch on solar, but wind and hydro. So the same thing could go for a nuclear power plant or whatever kind of power plant, 0 or 1. And there can be kind of planned outages. And then based on the historical data, you can make this availability modeling. For example, I use this Poisson distribution in here. So Olkiluoto 3 service outage from 1st of March to 2nd of May. And that shows in the, if you go to Fingrid, sähköjärjestelmän tila, so the state of the network, it's going to show in there. Most important work activities: refueling, fuel inspections, leakage or leak tightness test of containment, isolation valves, electrical maintenance, reactor pump work, and such. So there's a lot of things to do due to this, even legislation related to that. This was, for example, from the, so another type of plant that can kind of go under this this maintenance. So all of these plants have their own maintenance cycles, but this is a good example since it's from Tampere, and what they had to do in Tammervoima was to ensure high availability. 2 superheaters in the waste incineration boiler were replaced during the annual maintenance in spring, and that's the superheaters in the pictures. So those were replaced in Tammervoima. And additionally, there was some Inconel coating in the boiler to ensure higher availability. So, yeah. Sorry? Yeah.
For a month?
Yeah. Yeah.
Do you have any idea of the contingencies which have been put in place to meet up with the cost of supplying such a large proportion of the power?
Well, so the question was, what are the kind of measures that have been taken to ensure that Finland has enough power during that outage? The fact that we have these links to Estonia, Sweden, Norway, that's going to be sufficient for us. And this time of the year usually doesn't have such cold spikes. So, but you're right in essence that if there were a situation where there was no wind and there was really low temperatures, so let's say -30, and Sweden would have a similar situation, then at least our prices would go way up. But Olkiluoto 3, we have a lot of this, let's say at least 1,000 megawatts of this gas turbine facilities or gas turbine production fleet. So that is one way to kind of mitigate this kind of a situation. But yeah, it's a good question since it's 1,600 megawatts. So related to maintenance, you have this kind of a U curve. So there's preventative maintenance, condition-based maintenance, and corrective maintenance. So if you don't maintain your facilities, the operating cost is going to go up because you're going to have to do a lot of corrective maintenance. But if you have this preventive maintenance, then the operating costs are going to stay low, but your maintenance costs are going to be high. So the sweet spot is somewhere in the middle. So condition-based maintenance. This availability modeling, this can be as simple as using, for example, this Poisson distribution. So you can say that for each failure, the availability of the system is set to 0, unavailable, and the rest of the time it's available. It doesn't have to be utilized, but it's available. So you can say that that's 4th year in my inspection cycle, and you can see there are dips. So you can say based on the historical data of, for example, nuclear power plants, these kinds of incidents have been happening, and the duration of them has been something. With nuclear power plants, it would be a lot longer outage than in here. In here, I set the outage from 1 to 5 days, for example, and certain distribution to give me a probability when there is going to be an outage. And then you can apply also this kind of a wear and tear of the systems. So in my case, with my Python plant availability degradation code, what it does, it's going to give me more outages towards the end of this inspection cycle, because I defined in the code that there is going to be more wear and tear for the system. Well, this 10-year time frame and this outage percentages, they are completely arbitrary, but this is a way to do it. So if you have historical data, you can make fits based on that. And for example, in here, if you're going to make this, if you want to make this uncertainty representation, you have to use, for example, some kind of a distribution in there. And this Poisson distribution is one. Weibull distribution, for example, is something, and I kind of combined the effect of this aging and this Poisson distribution. So it changes every year. It's going to be worse and worse and worse. So the failure model, use of Poisson distribution for this failure modeling and this random outage duration aligns well with this kind of stochastic modeling techniques. So it would give me maintenance hours as a function of time. And as I said, this is completely arbitrary. Most power plants wouldn't function that they would have such many outages in 10 years. So that wouldn't be profitable. So you can integrate this kind of modeling with these optimization tools such as Spinopt in a way that you export a time series. During my 1 year, it's going to do this. And of course, if you want to make this Monte Carlo simulation, you can make multiple of these different sets of outages based on that distribution that you have. So that's one way of tackling it. So that was related to this production. So you have changes in, for example, the availability. You have changes related to these efficiencies that you can take into account with linear fits, for example. So what comes to transmission, electricity and district heating networks, dynamic effects that influence those? You have this power flow dynamics, grid frequency regulation, voltage fluctuation, and reactive power effects. We're not going to go into this reactive power effects. That's a bit more on the electrical engineering side. But the voltage fluctuate or the two other, but this grid frequency regulation is ongoing all the time. So it's this really second scale adjustments in the production and also sometimes in the consumption to make the frequency meet this 50 hertz. Thermal losses, district heating networks, they are much lower in operation and they don't require such delicate control and balance as this electricity grid. But either way, that's one dynamic effect that has to be taken into account. And since it is so slow, then you have to take, if your network is elongated type, so production is here and the consumption is in here, there's going to be a time delay there. Network congestion, so there might be some bottlenecks that form when you're trying to transfer electricity or heat. Load shedding and curtailment. I don't think Finnish electricity network has had too many instances of this load shedding. So it means that would be actually what happens with if there's too little power production due to this Olkiluoto outage. It would be that the operator decides or the automatics decide that, okay, let's ditch that load. So some factory is going to run out of electricity now. Curtailment happens with renewable energy. So if there's too much production, and this is also related to this network congestion. So if you don't have enough room in the transfer lines, then you're going to have to do curtailment. And that's the problem with Finland having all its wind power production in the western coastline, and the most amount of consumption is in the Helsinki capital region. Failure repair dynamics. So components and failures introduce system-wide delays and require these dynamic responses. So related to this power flow dynamics, there's also ramping in here. So you have ramping effects or ramping constraints related to single power plants, but you also have ramping effects or constraints related to these power transmission lines. So refers to, in this context, it refers to a change in power flow from one time unit to the next. So limits the allowed net flow variations of consecutive hours on specific lines. So in this modeling, it would include information about flow from the previous time step in the calculation. So you know the line, the transfer line power was this much, and now it's this much. Okay, it goes. So it doesn't necessarily increase or exceed the flow amount that's being allowed in the line. But if it's too fast, the change in there, then that's not allowed. High voltage direct current cables, they are subjected to ramping restriction of 600 megawatts. And so you cannot change. I'm not actually sure how this is at the moment, since there is this 15-minute interval that's being introduced in our electricity network. So this might actually be outdated information. So be aware that the electricity network is changing from hourly interval to 15-minute interval, but it doesn't yet show to the consumers. And I tried to find information, when are we going to go into this 15-minute, so you can buy electricity from the spot market with 15-minute intervals. But for the consumers, it's not yet available. There are some specific cable restrictions also, I think it's this Norway-Denmark cable 450 and this Polish link, I think in here is 300 megawatts. So transmission system operators have stated that frequent large changes in production and flow in the grid make it more difficult to control the frequency. So that's why there are these kinds of ramping rate limits. And so this would be basically the ramping rate limit in graphical form. So if there's a step change in the so commercial flow and physical flow, so you cannot exceed a certain ramp in here in the physical flow. So that's going to affect the commercial flow. And frequency quality split out to causes and mitigation measures. So ramping restriction is one way to mitigate this structural imbalances. So that they arise from the difference from power or the consumption and production. So ramping restrictions is one way, and you have all of these marketplaces that mitigate also these structural imbalances. And now in here it's the 15-minute shift. So during 15 minutes, the ramping rate or the amount that you can adjust the load again is going to be smaller. So it's going to be more smooth, the transition during 1 hour. So power flow dynamics, and that is, for example, something that I think you can include in SpineOpt, so you can make these ramping restrictions also in there. In district heating systems, so this was from Juhani's work. So he calculated, for example, in this certain network that there was the idea, as we looked before in the exercises, if you're going to change this temperature control curve, so if you're going to lower the temperature in your network, that's being spoken in many instances that's what we're going to do. So this is the future. This is kind of like towards the net zero, but I'm not sure if this is really the way to go. As you saw before, what happens if you decrease the temperature? Yeah, sure, you're going to have less heat losses, but you are going to have more pumping constraint or the pumping losses. So the pumps are going to have to deliver more water, the same power. And the same power with more water means that there's going to be more flow rate, more mass loss. So you can find these bottlenecks in these networks that there's going to be too much pressure loss in that. So in this network, supply plus return pressure drop over 4 bars per kilometer, and that was unacceptable in here. So you couldn't realize that even due to the network restrictions, and not even taking into account the substation changes that had to be made. So that can happen, this congestion can happen both in district heating networks and also in this electric network. So this is the network structure in a bit more detailed manner, and you can see there's a secondary plant and main plant in here. And actually what with this fluided heat, Juhani could calculate was that at what point in time, where do these kind of secondary and main plant flows meet? And at this instance, it was at this junction. And that's an important information related to the flow calculation. So this is in essence something that you have to do. You cannot just look these networks in terms of energy balances or power balances, that I'm going to balance out with these plants. If the consumers have this much consumption, then we're going to have this much production, and that is based on the merit order. Yeah, basically that would be the ideal case, but since there are these flow limitations, they have to be taken into account. So more more than just the merit order, the flow limits are going to affect this as well. So that's the dynamic modeling. You have to take into account not just what's been happened, or not just what's happening now in terms of power or energy. You have to take into account how much flow do we have in the pipes, how much thermal inertia do we have in the pipes, and that's usually a dedicated modeling program that you have to utilize. Load shedding, controlled reduction of electricity demand to prevent grid collapse when supply is insufficient. So if Olkiluoto 1 and 2 were the trip now, they would have to most likely start doing this. So hopefully that doesn't happen. But even, by the way, I checked from FinGrid open data, because I was trying to look for instances in Finland if there had been this load shedding had been done. Causes: sudden power plant failures, Olkiluoto 3 in 3rd of July 2024, 3rd of June. Insufficient generation during peak demand, frequency deviations typically below 49.5 hertz. So the goal is to keep the frequency in 0.1 plus minus limits. So this would be also already a really big decrease. So 3rd of June 2024, what happened was Olkiluoto tripped out of the network and the frequency dropped. So there was too little power production, but it didn't even go under this 49.5. So I don't think they had to make any kind of actual load shedding. There can be manual load sheddings or automatic under frequency load shedding, and there's also this demand response programs. But I don't know if this kind of classifies as actual load shedding. Renewable curtailment in electricity networks. Curtailment occurs when there's too much generation. So exceeds demand or network capacity. And not just the total demand, but the network capacity. And that's what's happening in Finland. So grid congestion or insufficient transmission capacity, overproduction when demand is low, stability issues, for example, can cause that. Grid expansion, that's what is being done in many cases in Finland now. Energy storages, that's one way. And flexible demand, encouraging consumers to shift usage to high generation periods. And that's what they have been seeing in Finland when you have these pricing curves, or the price curves related to production and also consumption. Usually the consumption curve has been rather inelastic in Finland. So now it's being tilted to the left. So you're going to see an example of that. That what it's going to mean with the prices and also with the consumption. But this curtailment, in essence, it's a bad thing because you're losing energy. And that's a figure I guess I have shown you before. So that is from the article in here. So curtailment energy share map, objective and quantitative measure to evaluate wind and solar curtailment. So in here, what they have shown is how much wind energy share you have and how much wind curtailment do you have to do. By the way, the physical curtailment, what happens actually there is either you break you have brakes in those wind turbines, or then you make the pitch control, so you actively change your blade angle, so it starts to stall. Or in these solar farms, I guess you can use this inverter control, and also you can just disconnect certain cables, not by manually plugging, but automatically. But whenever you have a network like Denmark that's close to Norway, that has a lot of energy storages, then what happens? You don't have to do wind curtailment, even though you have a massive amount of wind in your system. But for example, Ireland, it's a perfect example what happens at this if you have an actual island. So whenever wind energy share increases, so does the curtailment amount. And this should also show in your models. If you have this Monte Carlo type simulation, how much the wind varies and so forth, you should get curtailment in your models. So that was related to the production. So related to storages, what kind of dynamic elements do we have? That's actually what we have been going through. So we're not going to go through this one through in such a detailed manner. So energy storage operates based on this state of charge. And the state of charge, in essence, is differential equation calculation. But in your case, when you're doing it numerically in Excel or Python, it's rather straightforward. You just have to refer to the previous time step. We didn't take into account in our systems these ramping constraints too well, and we didn't take into consideration the efficiency the efficiency related to the charging and discharging of those batteries, but they affect as well. It's not a dynamic effect in essence, but that should be taken into account. So the round trip efficiency, but the round trip efficiency decreases over cycles. So that is also one dynamic effect that you have to take into account in your energy storage. So there's this self-discharge, that is one element. So you can say that the easiest way is that self-discharge is like 1% per 24 hours. In a thermal energy storage, that's of course not the case, because when the temperature decreases, so does the driving force of the heat transfer. So that would be not linear, related to the state of charge. But round trip efficiency decreases, and the self-discharge, thermal storage losses, heat over time, and also electrical storage. For example, these pumped hydro storages, you have losses due to solar radiation. So it's evaporating the water from the basins. So that's something that you have to take into account, and that makes this battery storage calculation in essence, it's already this kind of a dynamic model, but you can take into account these minute details that make it a bit more dynamic. Response time, some storage systems have a delay in ramping up and down their output, and optimization of charging strategy. So this kind of a dynamic optimization is something that we kind of saw in that exercise class that we did. We had some optimization algorithm, and that was utilizing this rolling horizon. And market price effects, that's something that I have an example on. I tried to make it complex in this is always a balance in these lectures, that I'm trying to make simple enough for people to understand in 15 minutes, but complex enough that it catches the system dynamics. And boy, that's a hassle. Market price effects. This was a really good publication or a picture from this publication that I linked in here. So this is an illustration how grid scale, so a large energy storage impacts electricity markets through price arbitrage. So arbitrage was that you buy when it's cheap and you sell when it's expensive. By changing or charging rather during low price periods and discharging during high price periods, storage smooths price fluctuations. It doesn't necessarily, well, it kind of shows in here as well. So in a perfectly competitive electricity market where everybody bids their operational costs. So the marginal price is related to strictly this operational costs and nothing more. So we have a demand, inelastic demand. So the price is this one. That's easy to understand. So that's the merit order curve, and that's the demand. So there we hit the demand. If we have more demand, we have more price. It's more expensive to produce. And usually this price curve, how did the AI put it for me? Since it's not convex, so it means that it's not linear. It's more and more expensive towards the end to produce the next unit of electricity. There's variable renewable energy, and that would be the profit of variable renewable energy. Since it doesn't have any operational costs, it has the highest profit in these cases. In here, the profit would be huge. If the gas turbines run the show, so the price is determined based on the gas turbines, the variable renewable energy is going to get a ton of money. Then, if you have a grid scale storage, what's going to happen is going to increase your demand. So it's also going to affect your price. So price goes up, and at the highest hours, highest demand hours, if you have your storage and you can discharge it, it's going to affect the price. So you can sell it with a lower price, but you're still going to make profit. So this was in this article referred to as welfare. So how much the electricity kind of market benefits from this storage. The prices in here are going to go, or the profits, they're going to go up in here. The variable renewable energy is going to lose this amount since the production. So let's see. The production was at first this one. Now, when the battery is going to increase the price, I'm going to show you with the mouse in here so the Zoom people can see it as well. So before this was the profit in here. Now it's going to increase by this much. And also in here, you're going to decrease your profits because the price went down. You had this much more profit, so your total profit is going to only be affected by this darker gray area. And this is what the consumers kind of say. For this, you don't have to pay anything. Then that's what the battery energy storage kind of wins. How much profit does it make? So there's also an example on this source on what if it's not an ideal market, that not everybody is bidding according to their kind of operational costs. But this was a really good example. I used the same nomenclature as in the source, so you can see the term definition from here. And I would encourage to go through and try and understand this bigger. So that was related to these market price effects. And in Excel, I had, let's see, this one. So this was what the battery does. So as I said, it's really, really hard to kind of come up these examples out of thin air. But I made a merit order curve. It's not like it's a bit more linear than I would have wanted it to be, but during the hours of the night, it's not always clear what you're after. So this is what came out of it. So this is what we did before in the exercises. So merit order curve just means that if you want to produce the next amount of electricity, you're going to have to increase the price, because this is going to be the operating price of this fleet in here. And there's the demand. It's inelastic. The demand is based on, for example, outside temperature. So it's fixed. We're not going to have any kind of flexibility. So what the battery does, in here, I have 24 hours. I have a consumption in here. I made a sine wave out of it. So if I were to draw this consumption, do I have it in here? No. Let's draw the consumption. You're going to see that it's a sine wave. And I can modulate the amplitude in here. So it shrinks the amplitude and so forth. But let's put, I have a kind of a charge and discharge strategy in here. So that's related to the electricity price. So there's going to be moments where the price is high. There's going to be moments when the price is low. This is a very bad strategy. This is done manually. But you're going to see that when I have this charge and discharge, and if I have this battery charge rate, and it's going to be zero, we're not going to do anything. The price is going to be dictated purely by the merit order and the consumption line. This consumption line, by the way, it changes based on this consumption. So it just moves to left and right. And whenever I start putting this battery charge upwards, we're going to charge and discharge with 200 megawatts. And we have a battery maximum state of charge of 6,000 megawatts. I just manually check that it doesn't go over that. So there's the state of charge. So what's going to happen in there? In here, it's going to increase the price because it's going to move the merit or the demand curve in the merit order function or merit order figure. It's going to move this curve to the right. So it's going to ramp up the price. And what happens when you discharge it? It's going to decrease the price. So in essence, what's going to happen if I were to have an optimal discharge and charging strategy in here, let's see, it's going to start kind of bringing the electricity prices to a level. So that's the market effect of large-scale energy storages. We're not going to see that yet in Finland, I guess, but rather we're going to see how they affect to these reserve markets. But that effect is going to be rather soon saturated. There are so many battery energy storage kind of companies that are flooding their products to the reserve markets that the effect is going to be rather soon, or the market is going to be rather soon saturated. And then somebody's going to start to bring these into this spot markets as well. So this is what it would affect the spot market. It doesn't do anything in this spike because I didn't say to charge or discharge. So I could say that let's charge more in here and let's discharge in here. So yeah, that's what happens. We charged a bit more in here. So let's put 500 megawatts in here. Now it makes it a bit more flat. So the price effect in electricity spot market of large scale energy storages. So in here you can see it brings the higher prices down and it brings the lowest prices upwards. So in your case, you would just have to have in that Excel that you made in your Moodle assignment 2, you would have to have a state of charge vector in there, and then you would have to have some kind of a strategy that when the electricity price is low, let's charge, and when the electricity price is high, let's discharge. So that's going to start balancing out the prices, and that's rather easy to implement in that model. The difficult part, of course, is trying to see how the merit order changes then. But in this case, I didn't put any kind of a price for the battery, so it's just operating when it's too cheap or too expensive, and it narrows down the prices. So related to consumption, these dynamic effects, we have time varying demand, electrification and load growth. That is a long-term scenario. We're not going to cover that in here, but we're going to have more electric vehicles. We're going to have more electricity consuming systems, heat pumps, industrial electrification, those heat boilers and so forth. So that's going to go up. That's something that you would have to take into account if you were to model, for example, electricity price towards, let's say, in 20 years, 10 years. Demand response and load flexibility, what do those mean? So time varying demand, this doesn't show too well in here. It looked a lot nicer when I had it not on this read mode. So 2023, apartment blocks, outdoor lighting, agricultural production and industry. I think this was mining and what else? There's a certain sector of industry that's taken into account in here. Mining and manufacturing, I guess, were these ones. So this is a certain type of nomenclature that they use in the EU reports. So time varying demand, that's something that you can kind of build based on these probabilistic models that we used in our consumption modeling, or just take time series. If you just take the time series, it's not going to be a dynamic model. You just have it as an input value. But how is the price going to affect to these? If you model that, then it's going to be dynamic. One aspect of this time varying demand is what we saw in our district heating system modeling. And this was the measured and modeled demand. We had during the summer hours, we had the fit in there. So that was based on this data. So that this is the data-driven part. Or actually, it's also during the whole year, but that's where it was extracted from. So we made this fit for the hot water consumption. And then the other one, during the other hours of the year, it was outdoor temperature driven. So there was this physical model. But if you go to this article, let's see if I can open it from here. they also have a differential equation that they take into account in here. The structure thermal inertia. So that's why there is mCp dt dt. So this, or dou T. The partial derivative of mean temperature of this wall as a function of time. So there's the mean temperature of wall, ambient temperature, inside temperature. In and out, they refer to these resistances, I think, of the heat transfer. So this makes it a differential equation. And what they are taking into account in here is whenever you're heating up your house, there's going to be a certain lag because the walls absorb part of the heat and they act as a heat storage. They act as a heat buffer. So if I were to activate that in my model, let's see if we can see any kind of a change in here. If I were to activate that model in this calculation, actually it's activated now. So if I deactivate it, you can see that the red curves change ever so slightly. So if let's put more of this rho, so density of the structures. So it means that it has more heat capacity. If it has more heat capacity, it means that the fluctuation in the temperature is going to decrease. So again, if you were to make more precise modeling, you have to take this dynamics into account, that there is going to be some heat storages. And you can see the black curve in here is the thermally thin model that doesn't take that into account. And the thermal inertia is being taken into account with the red one. And you can see it's from 2000 and 2200 between that hours. So you can see there's a lot of fluctuation between the model and the measured values. But either way, our profile is ever so slightly being kind of decreased in terms of amplitude of the temperature change in here. So that's one aspect related to this time series, or rather time varying demand. So load flexibility refers to the ability of electrical loads, or maybe even heat loads, to adjust their consumption patterns in response to grid conditions, market signals. So this is the ability. Load flexibility is the ability. Load shifting, so moving consumption from low cost to off-peak hours. Load shedding, so you can just shut down the lights if it's too expensive. Fast response flexibility, adjusting consumption instantly for grid stability. Industrial flexibility, factories adjusting production schedules. EV smart charging. You don't charge during the day when there are peak hours. You charge during the night when it's cheap and there's not too much consumption. And heat pumps and this air conditioning, for example. So demand response is when you, based on market signals, use your load flexibility. So consumers react to dynamic electricity prices. So that's what we are doing in my home as well. If the electricity prices go high, I don't put on the oven. Incentive-based demand response. Utilities or grid operators, they pay consumers to adjust demand. And this, in my opinion, is a good thing, and the companies should offer more incentives to do this. And there's automated systems for it. I can give my heating system control to the grid operator and say that whenever there's too much demand, you can decrease my heating electricity consumption in the heating, but you're going to have to pay for me. So that's the incentive-based demand response. So industrial loads participate in grid balancing in Finland. Consumers shift consumption based on spot market prices. and industrial users reduce demand when requested by the grid operators. And in here, we have demand response. The graph illustrates how flexible load demand side response can reduce electricity consumption when prices rise, effectively shifting the demand curve. So the more the demand curve is tilted to the left, the more flexibility you have. And what it does to the price curves. If you have a perfectly inelastic demand scenario, so the curve would be upwards, a vertical line, there would be no demand response. However, if you determine, let's make a really simple example. We have consumption flexibility in here. Let's put flexibility to 1, so that's so small that it doesn't change the curve slope too much. For some reason, yeah, my Excel doesn't seem to be updating these curves, and I'm every now and then wondering what's happening here when the calculation doesn't go through. So my price is just based on the merit order curve. So whenever we have a certain amount of consumption, this is again a sin curve, we're just going to move this red line to see wherever the price is. That's the easiest way to do it. But when we have more flex, so let's start flexing, what it means that these consumers, they have the ability and they have the willingness. It has to be both. They have the ability and they have the willingness, or somebody is forcing them to do it. So whenever the price is high, they say, well, I can decrease my load a bit. And what it means that if our price was now on this level, so 30 or 35, it's 30, and I'm going to put more flexion in here, it's going to drop down into here. And now, again, if I update this curve, you can start to see that it's going to start shrinking down. All the differences, the peaks and the valleys. The peaks are going to start shrinking down and the valleys are going to start lifting up. And boy, was this a hassle in Excel to do. So we'll see if this is anyhow sensible to do it in Excel. But you can also see in here what is actually decreasing the prices. We are decreasing the consumption. So consumption flexibility in this case means that actually in here the valleys are not being lifted. We don't have like incentive in the kind of low price hours to start doing anything useful. So this would be the electrolysis or fuel production or whatever that utilizes this one. So that would actually lift it up. So I said incorrectly that it started to lift up these valleys. That's not what's happening in here. It's just decreasing the consumption. If we include both battery and this flexion, so let's put flex to 1 and charge to 0, and now it seems to be updating. So everything is just based on the merit order in here. We increase the flex, so it decreases the valleys because there are consumers that are willing to tone down their consumption. And now when I have the battery also in here, I have some kind of a charge and discharge strategy. When it's cheap, it's going to start bringing up the prices based on this idea in, let's see, in here, this one. So prices go up when it's cheap, prices come down when it's expensive. So both of these these flexibility and the battery. So the demand response and the battery, they are able to level out the prices. And if we had an ideal system, the price could be flat. So how much do you want to pay for that? Because especially the batteries or the energy storage systems, they come with a price. And also the consumers are going to start requiring some incentives, so money for the demand flexibility or the demand response rather. But that's all the time we had today. We'll continue on these issues tomorrow on Friday on the exercises. And remember, Moodle exercise 3 is on the Moodle pages now. You can complete that one. And I'll put the SpineOpt installation guides and the kind of assignment also for to the Moodle pages, so you can see that in advance and start familiarizing yourself on what we're going to be doing. And remember to download these information. Okay, but let's stop here so we don't go over time. Thank you for listening.